Sorry. Well, good afternoon. It's already 12:21. We're supposed to start at 12:15, but right now I'm the only one in the class. This is for Calculus 3. Of course, this is Monday, the 1st of October, 2018. So I guess I'll get started without anyone else here. Just as far as announcements went, just the regular three that I've been announcing last week. If you're graduating anytime soon, you really need to get your application for graduation in. If it's this term, it's got to be in right now. I mean, as soon as possible. If it's next term, this is a great time to start the application process. So that gives you time in case, to schedule classes for next term to make sure that you will graduate on time. So if you are graduating next term, this is the best time to start the process for your application. Then the other two were that they are looking for note takers, and they will pay you to take notes for students who are some way incapacitated and can't. And also they're looking for tutors in the Space Center, perhaps in Student Support Services here too. We have both Space Center and Student Support Center services, and on the Birmingham campus I think it's just mostly the Space Center. But they were looking for tutors, and they'll pay you to tutor. And you set your hours however you can to match the other students, but it's completely up to you. So great opportunity. Take advantage of it. All right, we are in Chapter 12, Vector Valued Functions, where we've been for a while now, and we're in the last section in it. I'm pretty sure this is 12.5, Arc Length and Curvature. Okay, now objectives for this section of Chapter 12 are to first find the arc length of a space curve, to use the arc length parameter to describe the plane curve or the space curve, to find the curvature of a curve at a point on the curve, and to use a vector value function to find frictional force. That's an application type for that. Okay, so let's first look at the concept of arc length. Okay? The formula for the arc length of a plane curve has a natural extension to a smooth curve in space, as stated in this theorem here, Theorem 12.6. The arc length, now, in the text, you had a little bit of a precursor that went before this. And perhaps I ought to go back to that too. I was thinking they were going to show this, but they obviously are not. Back in section 10.3, well back there, you saw that the arc length of a smooth plane curve C, given by the parametric equations x equal x of t, y is equal to y of t, where t is going from A to B, that curve, let me get my pen set up. Okay. That curve was S is equal to the integral from A to B, these are the limits on t, of the square root of x prime of t squared plus y prime of t squared, okay, times dt. Now, and in vector form, r of t is equal to x of t I plus y of t j. Now, back in chapter 10, we weren't dealing with the vectors at that time. Now this is just a little bit of an extension to get it in the vector form. So you can also express that equation S as the limit from A to B of the magnitude of R prime of T dt. Okay? Because that's exactly what R prime would have been. Okay? Now, extending that to space is then what they were showing here in this theorem. S for a space curve now is the same limits, limit from A to B, T's going from A to B, of square root of x prime squared plus y prime squared plus z prime squared, which would be exactly what the integral from A to B of R prime of T, the magnitude of R prime of T squared, dt. I mean, not squared, just R prime of T dt. All right. That in mind, let's do example 1. And by the way, example 1 could be, can be viewed larsoncalculus.com for an interactive version of that type of example. Okay? So let's do example 1. Boy, jump right into it here, don't they? Find the arc length of a curve given by ti plus 4/3 t to the 3/2 j plus 1/2 t squared k. That's a rather strange looking equation just to pick out of the blue, and I'll tell you now, they didn't just pick it out of the blue. Okay, they had to pick one that would fit all the criteria, and they want to do this from t equals 0 to t equal 2. So you want that arc length that comes up and twist around like this. Now, it's not particularly easy to see that is a curve, and indeed it is. In the I direction of the x-axis is coming out here in a linear sense. In the j direction, the y direction, it's going in a t to the 3/2 sense, which is and then multiplied by 4/3, which expands it a little bit, stretches it a little bit that way too. But the you're going at t to the 3/2, and then in the k direction, you're going up by the square of t, which would be the fastest, but then you're doing a 1/2, which slows it down a little bit, but that is the most rapid expansion. Now, we're only going from 0 to 2, so you don't notice the most rapid expansion in the k direction, or the z direction, as you probably would otherwise. So there's your the vector that describes the curve, and we want to know the arc length of that curve from 0 to 2. Sorry, I can't clear my throat. I don't know why. Of course, one thing we've got to do is find R prime. Okay, that's the first step, and that, of course, is I plus, and 3/2 of 4/3, or 4/3 or 3/2 is just 2t to the 1/2 power j plus t in the k direction. Okay, there's your R prime of t. Okay, what we want to do now, I'm so sorry. This is irritating. I know it must be irritating for y'all to listen to. I just cannot clear my throat. Okay, what we need is the magnitude of that R prime of t, which is the square root of the square of each of those coefficients. So that'd be 1, squared is 1, plus 4t, when you square 2t squared, t to the 1/2, you get 4t, and then plus t squared. So sorry. Okay, now you take that, and that's the square root of 1 plus no, it isn't. I was thinking that was going to be a perfect square. And it is not. Okay. If there had been a 4t squared, that would have been, and that's what I was thinking. I just glanced back up to make sure there was a coefficient of 1/2 there, and there is. So what we're going to do here is modify this ever so, well, modify it. And I'm going to write that as t squared plus 4t plus 1. Okay, just reversing the order of it, ascending to descending orders of your powers. And what we're going to do is take the first two terms there, and that would be t squared plus 4t. Whoops. I like to leave a blank after that. I don't think the book quite does it this way. And then a plus 1 here. And I want to complete the square there. Okay. Well, completing that square would be take half of the coefficient here, 2, square it, and you get plus 4. Okay. So that will be t plus 2 squared, but I added 4 there, so I also have to subtract 4 there, so I don't change what's under the radical. And this would be a minus 3. Okay. Now, if you're looking at that form, goodness gracious, for some reason this room has gotten rather chilly inside. My fingers are cold just holding the pen. Later I wouldn't be surprised if I won't get too hot, but this is rather strange. What this is going to lead to is a trig substitution. Okay? Well, I said a trig substitution. Doesn't quite look like one now. What they recommend, and is what I would recommend too, is going to a trig table rather, integration table, rather than, trying to work it out. Because, like I said, I would have been tempted to say a trig substitution, but theirs is actually a little different. I'm trying to find it. It's in, oh wait, I may have it. Yeah, back here. Integration tables, I had a thing holding my place in it. It's the square root, and this is a definite integral, by the way. Let me go on. This is what's inside the integral. So let me go on and do the integral. It'll be the integral from 0 to 2 of the square root of t plus 2 squared minus 3 dt. Now, when we go to an integration table, where I would suggest you look is, let's deal with it, indefinite integral for right now, and that would be the square root of u squared minus a dt. That's the place that I would I'm so sorry, I can hardly breathe here. In fact, I think I'm going to have to pause it and go down and clear my head. I'll be right back. All right, I'm back. I hope it's a little bit better, but I can't guarantee it. I wonder if I know I did finish eating lunch, and I did it rather quickly today, and maybe I just ate too much too quickly, and it just has messed up my breathing and my congestion and that kind of stuff. I don't know. And then to the room that's really cold, so they're all contributing, I guess. But anyway, here's what we're going to look for in the table. So if you go back to the table, it's in the second appendix in the text. And what we're looking for is forms that are either u squared minus a or the square root of u squared minus a. And if you look in there, in fact, I think the trig substitution would have been a u squared minus a squared, and that's why it's not a trig substitution, because it's a. But how you deal with that is you make it an a squared, where a is the square root of 3. So we will look for u squared plus or minus a squared. So that's going to be on page A4 in the appendix. In the appendix, it's Appendix B, page A4, toward the back of the book. It's going to be the form that's probably that very first one, 26, the square root of u squared plus or minus a squared. Now in this case, remember, our u is t plus 2, and our a is square root of 3. Okay? Yeah, and this gives us the form that they're dealing with. That integral is going to be, I'll put my 1/2 out front, and then the u is t plus 2 times the square root of t plus 2 squared minus 3, exactly what our integral there is, integrand there is, minus your a, remember, is square root of 3. I'm sorry, I jumped down a line here I didn't intend to. That's a plus or minus. And let me back up. My finger moved while I was writing. Okay. Okay. Let's go back now. Okay. It's plus or minus a squared, which is going to be 3. And in our case, it's a minus 3. Okay, it's not plus or minus. It's a minus 3. I had it right the first time, but I had a square root of 3 there. Okay, the log, natural log of absolute value of the square root of 3, that's your u. No, I'm sorry. T plus 2 is my u. T plus 2 plus the square root of, just like before, square root of t plus 2 minus 3. Okay? That should be in absolute value bars. Plus c. Okay, we don't need plus c. That's where we evaluate from 0 to 2. Okay? Now, I hope I wrote it down right. I think I did. Okay. So let's see what we get. And the 2 and the 0, remember, are the limits on t from 0 to 2. Now, one thing I think we can take care of right off the top is, Well, maybe not. I was going to say, I'm sorry, we can do it. Forgot that's a square there. I'll make sure I wrote it as such. Yeah, it's u squared, t plus 2 squared. Okay. Got it. Okay. Now, this absolute value bar, since t is going from 0 to 2, when t is 0, that first thing is a 2. When it's 2, it's a 4. Okay? So those are both positive. We're adding to it something in t plus 2 squared is going to be positive, and the minimum value it would be 4 when t is equal to 0, but 4 minus 3 is 1. So that's going to work fine. So we won't need the absolute value bars. Okay, so I'm going to take them off just to keep them from being too confusing here. Okay, because that one almost didn't look like absolute value bars, and it should have been. Okay, so now let's evaluate. Okay, okay, it's going to be a 1/2. Okay, that's there. Now let's put in t equal 2. So 2 plus 2 is 4, high level math today, times the square root of, that would be 2 plus 2 is 4 squared. It's 16 minus 3 is 15, square root of 15, minus 3 times the log of t plus 2, that would be 2 plus 2 is 4. Okay. Now, when I took off the absolute value bars, needed to put back in some sort of grouping symbol so you have all that grouped together. Log of 4 plus, now when t is 2, that would be the square root of 2 plus 2 is 4 squared is 16 minus 3 is 13. I think that other one was a 13 too. I don't know where my brain is today. I think that's a 13 there. Okay. Let me see and make sure. Yeah. Okay. 4 plus 13. Okay. Positive number. Minus, this is all still inside the parentheses, minus 0 plus 2, so that would be 2 times the square root of 1, which is just going to be a 1, minus, which is make it a 3, plus 3, the log, natural log of, and that would be a 2 plus the square root of, that's just going to be a 1, okay, if I'm doing the math right, okay. Now, I need some more room, so I think I'm going up to the top. That's going to be 1/2 4 root 13 minus 3 times the log of 17, all a positive number, minus 2 plus 3 log 3. Okay. Now, that's not a very attractive looking number by any means. Trying to think if there's any way to simplify this. The minus 3 log 17 minus a minus 3 log 3 don't really think there's any way to satisfy that. So let's see what we've got. Okay, they did the t plus 2 over 2. Yeah, that's fine to do it that way. Times the square root of that, minus 3 halves, which is fine to do it that way. They put the absolute value in there. They really didn't need to. And anyway, that came up 2 times the square root of 13, which is what we have, minus 3 halves times the square root of, oh, that's, sorry about that. I left off my square root symbol there. I have it there, but I didn't plug it in. So this is okay. 4 plus root 13. Okay, sorry about that. All right. Minus, and then 2 times minus 1 half of minus 2 is minus 1, and then plus 3 halves log 3. So yeah, we've got exactly the same answer they did. Now that I may put my square root of 13 back in there. And you can plug in and actually do the math of that, and you should get the same answer. Something about 4.816 would be the arc length of that. Now, they didn't give any units, so that we don't have any units for it, but whatever unit you were measuring on your axes, that would be the unit that you're doing here. Centimeters, meters, inches, feet, yards, furlongs, whatever. That would be the length you would have. Now, I thought, I was going to say this, they came up with such a weird looking original R function, and I thought the whole reason they were doing it, so when you take a derivative of that function and then square each of the components of that derivative and then take a square root of that, you would get something that would be integrable. Yeah, you had to do all that, but still wound up with something that wasn't integrable very easily. So all my prognostications were incorrect on that. I just finished showing example 1 at the bottom of page 855, but I was going to now show how the book did it. I think it's very similar to what I did. I was going to say we did, but it was like we in the room.
I see it's just only me.
What's that?
I see it's just only me.
Yeah, so far. Okay. And hopefully some more will be coming in, but it's getting a little late. But you showed up, so maybe some of the others will too. And let me mark you here. And happy October, by the way. Oh, really?
Yes.
Yeah. How old would you be?
22.
22? Nice. Okay. And I know you're registered to vote, aren't you?
I am.
You are, and you are going to be voting in November. Excellent. Okay. So I've just done all this, but I'm going to now go to a new slide, and you'll see how they did it, which should be very, very similar to the same way. Okay? Now, I see no reason to have changed all this, but they did. Their problem was an R vector, which was ti plus 4/3 t to the 3 halves j plus 1/2 t squared k, and then they went and changed it to x, y, and z, which is fine, perfectly fine, and then take the derivative of that, which you could have done at the original function, just like they had it, which is what I did. Derivative of this, of course, is 1. Derivative of this would be 3 halves times 4/3, and that would be 2t to the 1/2. That's what they've got here. And then this one would be, take a derivative of that, would just be a t. Okay? which is what we did, but I kept it in our vector notation rather than splitting it into component notation. But both ways work, okay? Now, so the arc length from 0 to 2, which is what the problem asked for, t equals 0 to 2, is given by, and they went through and then put these functions, the square root of x prime squared plus y prime squared plus z prime squared, using the ones they had there. Whereas what I did is just take magnitude of r squared, r prime squared, which gave you exactly the same thing. So it works out the same, whichever they did. Remember that these numbers are the limits on t. So there. So let's plug in what we found the x prime, y prime, and z prime to be. And that z is equal to the limit from the integral from 0 to 2 of the square root of 1 squared is 1 plus 2t root t to the 1/2. When you square that, you get 4t. And then the last one is just t squared. Okay. Now, before you came in, as I was saying before on the thing, I thought for sure they had chosen such a weird little vector to be doing this to. I thought for certain the reason they chose that vector was so they'd come up with something that would be a perfect square under the square root. But no, it wasn't. So without that, now we have to do an integration of that. And the best way to start that is by rewriting it in descending orders of the power, which they didn't do, but they did it, but they didn't show it. And if you write t squared plus 4t and separate that off from the plus 1, and then complete the square for t squared plus 4t, that would be adding a 4 to it. So inside the radical, you have to also subtract the 3 from it. Subtract the 4 from it. But you already had a 1. 1 minus 4 is minus 3. So that's where that came from. Now they went to a table in the back, which is what I recommended, because at first I was thinking this could be possibly a trig substitution, but no, it doesn't turn out being one. It is its own problem, but you go to the table in the back, and this is how that translates. You use u minus a squared. Of course, you don't have an a squared, so this becomes, for that to be a squared, a must be the square root of 3. That would be your u, square root of 3 would be your a. And you've got the minus sign there. So if you go to the integration table in the back, you'll see that you get a u over 2, where u is t plus 2 over 2, times the square root, exactly this integral here. They go back and call it u squared, blah, 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 blah. It's exactly that integral. Radical. Okay? Then, that's the first part of the solution, minus 3/2. Now, in the integration table in the back, they have the 1/2 out here. Okay? And the book has distributed 1/2 in here, which is perfectly fine, but that's not how I did it. I left the 1/2 on the outside. So 3/2 times the log of, and this was your u, okay, like that u, plus, and then the same integral that we had here, square root of u squared minus a squared, which comes up to be exactly that. So this they put in absolute value bars, which I find totally unnecessary, and here's why. Look at what's in here. The minimum value that can be is when t is equal to 0. That would be log of 2, plus the square root of 2 squared, which is 4, minus 3, which is 1. It's the minimum value of it. 2 is going to be even bigger. So that's never negative. So you don't need the absolute value bars for this problem. Some you might, this one you don't. Okay? And then this is a definite integral from 0 to 2. So plug in the 2 first, and this would be 2 plus 2 is 4, over 2 is going to be 2 root 4 squared minus 3. That's 16 minus 3 is 13. So this is root 13 minus 3 halves the log of 4 plus the square root of 4 squared, which is 16 minus 3 is 13 again, square root of 13. And then plug in the 0 and you get 1, and this will be 2 squared, which is 4 minus 3 is 1, square root of that is 1, so this is going to be 1 minus 3 halves of log of 2. So plug in 0, log of 2 plus, and then again that's square root of 1 is 1. Okay, so log of 2 plus 1 is 3. Okay, and that's what they wind up with. 2 root 13, exactly like we got, minus 3 times the log of 4 plus root 13, that was this part, the 2 plugged in, minus 1, let's see, yeah, when this is 0, this would be 1, and this would be the square root of 1, which is 1, so that's just minus 1. And then minus a minus is 3 halves, and like I said, this is log of 2 plus 1 is 3 log of 3. All right, and if you want to go and plug all these numbers in, 2 times root 13, will be a relatively large number. Root 13 is between 3 and 4, closer to 4, so this is going to be close to 30 or so. Okay, minus 3 times the log of a pretty good sized number. This would be something greater than 3, closer to 4. 4 plus 4 is 8, so something around 7, log of 7. It's going to be a moderately, not a large number, it's a number. Subtract 1 from that, and then add that, and you wind up. And log 3 is it's less than 1, but 3 halves is greater than 1, so you get enough of a plus there. You come up to 4.61816. All right. Mohammed is here. All right. Now, I hate to do this. How about seeing me right after class? So anyway, there's the same answer we got. I got it.
How did you get 16?
How do you get the what? 13?
Yeah, for
13. From here, when you plug in 2, 2 plus 2 is 4. Squared is 16, minus 3 is 13. So that's what it came up there and there. So it shows up here, from here, and there, from there. This is 4. 4 plus 3. Okay. This is the example 1, bottom of page 855. Excuse me. Okay. Let's see if they show example 2. No. Okay. So let's back up and try to do example 2 here. Okay. Finding the arc length of a helix. So find the length of one turn of the helix given by R of t is equal to b cosine ti, okay, plus b sine of tj plus the square root of 1 minus b squared t Oops. Okay. The square root 1 minus b squared times k. All right. Now, there's your helix. Of course, cosine t plus b sine t is going to be a circle of radius b. That would just be the I and j part. And then you're going up square root of 1 minus b squared. So one thing you notice right off the top, b has to be between minus 1 and 1. Okay? And I would say it's a pretty good bet that you don't want b to be 0. Okay, so, well, actually, yeah. So it has to be something between minus 1 and 1, but not 0. So, well, actually, no. It would be fine for b to be 0. Okay, sorry. No, it would. If b is equal to 0, this is 0, that's 0. And that, oh, that would be one thing. Yeah, it would be okay, I guess. It wouldn't be very interesting, but it would be just a line going up in the k direction. Okay. But I still don't think it would be all that interesting. Okay. So, what are we going to do first? To find the length of one turn of the helix. Now, one turn of the helix, what does that tell you? T is going from one turn of the helix. Cosine t, sine t, what gives you one turn? Zero to 2 pi. That gives you one time around the trigger, right? So your t is going from 0 less than or equal to t is less than or equal to 2 pi. Okay, so that gives you limits of your integration. Okay? Now, you want arc length. Remember the formula for arc length? Y'all, neither one of you come in when I went over it, so you know what it is. It's the integral. Here is a shorthand way of saying it. Of the magnitude of r prime of t dt. Okay? A little bit longer way of saying it is the integral of the square root of x prime of t squared plus y prime of t cubed plus, no, wait. X prime of t squared, y prime of t squared plus z prime of t squared, okay, dt. It's the magnitude of the r prime vector. Okay, that's what this is. So it'd be the square root of this one squared plus that one squared plus that one squared. Okay, so what seems to be, and by the way, this is going from 0 to 2 pi, this is your limits of t, so this would be definite integrals from 0 to 2 pi. 0 to 2 pi. Okay? Now, what's going to be your first move that you need to make? What do you need to do with it? Take a derivative. Good choice, right? So let's do r prime of t, and that would be what? Negative. B, no, B is a number, not a variable. So it just be B, right? sine t I plus v cosine t j okay. Okay. Yeah, it square root of 1 minus b squared. Yeah, because that, wait. Is there no t in there? Yeah, there is a t in there. I just left it off. 1 minus b squared. Okay. Okay. Goodness, my eyes ache. And remembering, b has to be between negative 1 and 1, okay? And it won't make a lot of sense. Well, it could be 0, but between negative 1 and 1, okay? Because otherwise, your radical there is negative, so can't be negative. All right. Now, we've taken the derivative, and what do we do with it? What do we do with it? Yeah, we want the arc length, and that's going to be called S, is equal to the integral from, yeah, I guess I should have put that here. S is equal to integral from 0 to 2 pi of, okay, this first one squared. When you square it, the minus goes away, so you got b squared sine squared t plus b squared cosine squared t. My writing is getting worse and worse. Plus that thing squared would just be 1 minus b squared, right? And this will be dt. Oops. What I forgot was my square root sign. Okay, so I don't really need this closing bracket because of square root sign. Okay, what were you going to say?
Since sine square and cosine square is 1.
Okay, yeah.
Can we just say dq?
Yes, that's exactly our next step. This will be factor out of b squared, and b squared times 1, plus 1 minus b squared minus, plus 1 minus b squared. The b squared is going to 0, and that leaves you just 1. Square root of 1 is 1, okay? And you evaluate that from, that's exactly where we're heading. S is equal to the integral from 0 to 2 pi of, and you want me to write all that down, or we've already determined? It's, write it down? Okay. The square root of, factor out of b squared, sine squared t plus cosine squared t, okay, plus 1 minus b squared, and that's all dt, okay, that is 1, so it's b squared minus 1, or plus 1 minus b squared, so this just simply becomes the integral from 0 to 2 pi of 1 dt, okay, which would be t going from 0 to 2 pi, and that of course is 2 pi, minus 0 is 0. So it should just be 2 pi. The length of that arc, one time around, is just 2 pi. Now that's because of how they chose to define our helix, okay? With this coefficient, but that is the coefficient of the t term in k, limiting this to be something between minus 1 and 1. Otherwise, that doesn't make sense. Obviously, well, it could be 0. And then, but when you do all this, the b squared minus b squared is going to turn to 0, which is 1. Okay? And evaluate the integral from 0 to pi dt, you just get 2 pi. Okay. All right. Now, the next thing is a thing that the books always love to do, okay? And it's a great concept, okay? Sort of a theoretical concept, but it turns out being an almost impossible thing to ever achieve practically, okay? And that's dealing with what they call the arc length parameter. There are a few examples that'll work perfectly on, so smoothly and so nicely, but in general, it's an almost impossible thing to deal with, okay? So let's talk about it. Let's talk this a little bit longer. I know I skipped some steps there. I was just running out of room. Because inside the radical here is b squared times 1 is b squared plus 1 minus b squared. Plus b squared minus b squared. Add the 0, you just get 1. Square root of 1, which is 1 dt. 0 to 2 pi. That would be a 2 integral t integral from 0 to 2 pi. Over the weekend, here or there, Saturday I did some work in the yard. And it was, we just had all that rain, so it was real easy to pull some weeds and beds and things that had gotten sort of out of control with all the rain we had. And I don't know what else happened, but I must have gotten some soil or something in my eye. I never noticed it, but now my eye is conjunctivitis, and ever since I've had the chemo for the leukemia, any little thing, and I'll get an infection, it seems like. So that's one reason my eyes are driving me crazy today, is this one does have some mild case of conjunctivitis in it. So I think that's part of why I was sneezing and doing that kind of stuff earlier. I don't know that. But anyway, let's go on to arc length parameter. We've already done this first example, because that was the second example. The arc length parameter. So here is the definition of the arc length function. Seems like a pretty reasonable definition. It's almost just like what we were doing. Let C be a smooth curve, like we were just doing, any kind of smooth curve, given by R of t, defined on the closed interval from A to B, just like the first two examples were. And for t in between A and B, where it's defined, the arc length function now becomes S as a function of t. Now, t is just a dummy variable that pulled out somewhere. And because of that, now we're going to do this function, rather than going from, back off, t is your original variable, but you're going to put that as the upper limit of your dummy variable u, okay? So you're not going all the way to A necessarily, but you're going from A to T, where T is somewhere between A and B. If T is equal to A, that's going to be 0, okay? And if T is equal to B, that's just going to be the arc length from A to B. But if T is anywhere in between, this is going to be the arc length as a function for how far you are between A and B. That's what the T is. And it's the same as before. The magnitude of your R prime of U du. Now notice before we had T's here, and this was your B up here. Now since we're moving the T up here, you have to make that a different variable, and you use their favorite, so they use U. And you do it just like before, the integral from A to T now, of square root of C prime of U squared plus x prime of u squared plus y prime of u squared plus z prime of u squared du. Now that's your S of t, and that arc length S is called the arc length parameter. Okay. Now again, nice little concept here, okay? But if you can imagine, it's almost impossible to come up with a function r that you can has these x, y, and z, not x prime, but x, y, and z coordinates, that when you take a derivative of them, square them, add them together, that they form a perfect square, so you can take a square root, and this comes out being something useful. That's pretty few and far between. In fact, almost impossible to do. Occasionally you'll run into one that will. So here's the curve, and they just show a generic little curve there. You can't tell where it's doing. It's starting not at the origin, but somewhere up here. It looks like in the xz plane, but it may not be. T is equal to a, and then it may be coming out here, bending back there. Who knows where it's going? This is a three-dimensional curve on the two-dimensional plane. Really hard to see what it was going. But that's represented. So at any point t here, your S of t is how long your arc is along that path. That's your arc length parameter. Okay. Now, using the definition of arc length function and the second fundamental calculus, you can conclude that ds dt, the time rate of change of the length of your arc length parameter, is exactly that integral, the integrand that you had there, which is the magnitude of r prime, which is your velocity, okay, or speed actually. So the rate at which you're moving along the curve, ds dt, is your speed. That's all it's saying. Derivative of the arc length function, okay, is the magnitude of your first derivative of your displacement vector. In differential form, then ds is equal to, you just take the dt, move it over here, the ds is equal to this dt, which leads you right back to the arc length function. S is equal to integral r prime of t, magnitude of r prime of t dt. So it seems like we've just run around in a circle here, almost literally. And in a sense we have. Now, the next example is example 3. Find the arc length function S of t for the line segment. This is a line segment now, in 2 space, not in 3 space. R of t is equal to 3 minus 3t I plus 4tj, where t is going from 0 to 1. Okay, so when t is equal to 0, this would be 3i plus 0j. So that would be where you start. Okay? And when t is equal to 1, this would be 0i plus 4j. You'd be up here. So this is because both of these are linear functions, this will describe a straight line, and there it is. Okay. So find the arc length function S of t for that line segment, and write r as a function of the parameter s. This r as a function of the parameter s. Notice s is a scalar quantity. It's a length. That's all it is. It's not a vector. It's a length. Okay? So we'll write r as a function of that parameter s. All right. Find the arc length. We're going to do that first, the arc length function. Okay? And how are we going to do that? That's one of the first things we're going to do. Take a derivative. R prime of t is equal to what? Say again? No, minus 3. No t. You take the derivative of this, you get minus 3, right? Minus 3. I thought you said ti. Minus 3i, perfect. 4j, you got it. Sorry about that. My hearing is so terrible. Okay? Now, there's your magnitude. What we want from there is there's your first derivative, your velocity vector, so to speak. We want the magnitude of that. Okay, and what would that be? Square root of what? 3 squared plus 4 squared, and that's the square root of second 9 plus that's a 4, yeah. 4 squared is 16. That's okay. Doing it on your calculator, 25. Square root of 25 is 5. All right. Okay. Got it. Took way too long. Okay. So there's your magnitude of that is just 5. Okay. And sure enough, you can see this. 3 squared plus 4 squared is 5 squared. You go 3, 4, 5 triangle. Yeah, so that's fine. Okay. Now, so find the arc length function s of t, and that would be s of t is equal to the integral from 0 to t now, not 0 to 1, 0 to t, of 5 dt, du, okay, because you have to introduce some new dummy variable, not t, okay, and what would that be? Second? 5u evaluated from 0 to t, and that would be indeed 5t. So there is your arc length function as a function of t. When t is equal to 0, of course that would be 0. When t is equal to 1, at t is equal to 1, this would be, well, yeah, it's up here. So the arc length variable would be how far you are along that between 0 and 1. That would be where you were along that curve. 0 to 1. 1 you'd be 5. So at any t in between, you would be at t at 1/2, you'd be at 2. Okay. At t equal 1/3, you would be at 1. T is equal to 1, you'd be at, so you have all those values in there. So that's your arc length parameter. I sure hope that's what they get it to be. Yeah. So this is a really easy one. I said a lot of them are going to be hard to do. This one was really easy to do. Okay, now, it says now write your r as a function of the parameter s. Okay? What you have to do here, you have r as a function of t, but t is a function of, s is a function of t, so what you have to do is get t as a function of s. So if s of t is equal to 5t, so in other words, s equal 5t, then t is equal to s over 5. Okay, be careful with your letters there. You don't get them looking. So now we plug that in here. R of t is equal to 3 minus 3ti plus 4tj. Okay. So r as a function of s would be 3 minus, okay, 3 times s over 5, because that's what your t is. That would be your I component plus, can't read my writing here, that's a 4t, 4 times s over 5. Yeah, s over 5j. Okay, so that would be 3 minus 3/5 s I plus 4/5 s j. Okay. So there's r as a function of s, 3 minus 3/5 s I plus 4/5 s j. Now, okay, the one thing we didn't do was do the parameter, okay, the limits on the parameter. Since t is going from 0 to 1, s is going from 0 to 5. So 0 is less than or equal to s less than or equal to 5. Okay. All right. For a linear function like that, it's pretty straightforward and fairly simple, I guess. Everything pretty much taken care of there. Okay. But I think you can easily imagine anyone getting into a more complicated thing, and you get real blue then, because it's very seldom they're going to come out that smooth. You know, the integral is 5, you know, and you don't have any t dependence whatsoever, or s dependence. I guess we beat that to death. All right. That was our example 3. Okay. All right, let's see how they complete the problem. Let's see. Goodness, it's so hard to see that small type. Oh, that's just the thing we just did. All right. Okay, they did the r prime minus 3t plus 4j, 3i plus 4j. Magnitude of that is 5. Your s is equal to the integral of the magnitude of your r prime. We know that to be 5, so that'll be, yeah, it's just 5t, s of t is equal to 5t, and using s equal yeah, that's exactly like we did the work. The magnitude was 5, period. Integral of 5 between 0 and t was just going to be 5t. And then using s equal 5t, you can then go back and say t is equal to s over 5. You can rewrite r using the arc length parameter, and that just gives you r as a function of s is 3 minus 3/5 s I plus 4/5 j. All right, and s is going from 0 to 5. Okay. Now, I want to make sure we're not skipping anything, though. This is theorem 12.7, arc length parameter. Okay. Now, this is a lot more generic, not as specific as the other. If C is any smooth curve given by R of S, now we're in arc length parameter. Okay? Not the one we just had, any of them. R is equal to R of S. The C is a smooth curve given by R is equal. And X of S I plus Y of S J. Or the other way of saying this, R of S is equal to S of S I, space curve with Z of S K. Okay, plane curve, just X and Y coordinates, space curve, X, Y, and Z coordinates. Where S is the arc length parameter, then the R prime of S, the magnitude of this, is 1. Okay? Wait a minute. Would that have been true in our last one? Let's go back and see. Okay? There was this. Okay? S going to 0 to 5. What is R prime of S? R prime here would be what? Negative 3/5 I plus 4/5 J. Let's take the magnitude of that, and that would be yes, 3/5 squared would be 9/25 plus 16/25 is 25/25. Yeah, certainly was there. Here they claim it is always. That is absolutely true. The magnitude of your speed, your R prime of S, the rate at which you're going with respect to S, is always 1. Moreover, if T is any parameter for the vector value function R, such that R prime of T, magnitude of R prime of T is 1, then T must be the arc length parameter. You can't have two of them. Okay, that's going to give you that. So if that were the case, then the T would be your arc length parameter. Okay, if that R prime of T, the magnitude of that is always 1, then that T would be your arc length parameter S. You wouldn't need the T, you could just call it S. Okay. Now we're getting ready to do curvature. Okay? Now, another thing I did over the weekend, between the pulling of weeds on Saturday, then I did a lot of walking on Sunday, and between the two of those I've got my knee. So anytime I'm in a position too long, it stiffens up on me. And as soon as I move around some, it's better. But boy, when I first stand up, it feels like that. It hurts. An important use of arc length parameter is to find curvature, the measure of how sharply a curve bends. For example, in this figure here, the curvature at P is going to be a very large number, whereas the curvature at Q is going to be a very small number. This is bending really rapidly here. This is hardly bending at all, but barely is bending there. More sharply at P than at Q, you can say the curvature is greater at P than it is at Q. Okay? That's sort of ideally. Now, what do we mean by that? Okay? What is curvature? You can calculate curvature by calculating the magnitude of the rate of change of the unit tangent vector T. Okay, the rate of change of the unit tangent vector T. That is going to be dt, remember that type of thing, with respect to the arc length parameter. So it's not dt, but dt ds is what we're talking about then. So our unit tangent vector at P, here's your tangent vector here, there, whoa. That is not right. Boy, this one should be curved about like there. That is a terrible drawing. Is that way in your book? It's awful. Okay, it's totally wrong. Okay? The unit tangent vector here would be about like this, okay? Now if you went back here, right at the maximum right there, that would be this one. So this T2 here would be at this place here, right at the vertex, you might say, of that curve, whatever that curve is. It's not a parabola, but it sort of looks like one. This T2 should be right here. Up here, it should be, the tangent vector should be in that direction. Okay, even though they've shown it poorly, the magnitude of the rate of change of t with respect to the arc length is the curvature of the curve. Okay, if you did the same thing here, say a point back here would be here, Q would be here, a point here would be here, they've hardly changed at all. So the rate of change of t up here would be very close to zero, not zero, but close to it. The rate change here would be extremely large. That t is awful. That is nowhere close. See, that looks like a tangent vector there. That certainly looks like a tangent vector there. This does not look like a tangent vector. It would be the tangent vector here. This one here would be about like that. Okay, so really poor. I'll try to draw this here. Now remember, these are unit tangent vectors, so all the magnitudes are 1. This one would be something like that, okay? If you had it down here, that would be the one that went there. So, lousy drawing, but you get the general idea, okay? I hope you do, okay? Notice the change here is great. Huge amount of change for a very small change here. Whereas here, that same degree of change, hardly any change. Okay. So here's your definition of curvature. Let C be a smooth curve, either in the plane or in space, either one, given by R of S, where S is the arc length parameter. The curvature K. Now this book calls it K. The last several books I've taught from called it kappa. The Greek letter kappa for curvature. This one calls it capital K. Fine, you can call it anything you want to. This curvature K, S, is the magnitude of the ds, so how fast the unit tangent vector is changing per unit change of S, okay? Which would be the magnitude of t prime of S. So that's ds, dt ds, not dt dt. Now, think about a circle. A circle has the same curvature everywhere, okay? Same curvature at any point, because its unit tangent vector is changing the same amount per unit arc length anywhere. Moreover, the curvature and the radius of the circle are inversely related. A smaller circle has to have a much greater curvature than a great big circle. So the curvature is and the radius of the circle are inversely proportional to each other, inversely related. That is, a circle with a large radius has a very small curvature. A circle with a small radius has a very large curvature. Yeah, that makes perfect sense. Right? Okay. Got it? Okay. Now, here's example 4. Yeah. Show that the curvature of a circle of radius r is, the curvature is 1 over r. Okay. Now, a circle of radius r, now here we start running into some little bit of a problem, okay? They use r for so many things, okay? Your vector r, which is your point that you're doing from your, say, the origin, that r is a function of, okay, of some parameter theta, okay? And of course, I think we know what that would be. Now, here's where we run into problems, okay? If this is a circle of radius r, that r has nothing to do with this r right here. This is just your displacement vector. Okay, well, I take that back. If this is from the origin, yeah, that's also your radius, okay? In a strange sense, it is the same. Okay, but this is r cosine theta I plus r, whoop, 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 not a vector. I'm so used to writing a vector symbol over r, it just came out naturally. Sine theta j. Okay. Yeah, a circle in two space. We're going to stay there. Okay, there is your displacement vector of any old circle, r cosine theta I plus r sine theta j. Guess we ought to draw the picture here. I don't draw circles very well. Okay, and I don't draw my lines very well either. So here's your displacement vector r, and at any place here, if this is actually your radius r and your displacement vector, this is your angle theta, then your x-coordinate here would be r cosine theta, and your y-coordinate would be r sine theta. Okay, and that works all the way around the circle. Okay, so there is your expression of r as a function of theta. Okay, now going back to trig, at least half of you, I know who your trig instructor was, so I will be most disappointed if you don't know the answer to this. How r and theta are connected? Remember? Say again?
Can you repeat the question? Can you repeat the question?
Okay. How are your arc length, your radius, and your angle connected? Now, your angle measured in radians, not in degrees.
Is that something to do with the origin?
Yeah, well, we're centering our circle at the origin, yeah. Let me go back to this question. What was your measure of radians anyway? Do you remember what that was? How do we define the theta? Okay, yeah, those are values of them, but, oh boy. Okay, if this is your arc length S, and this is your angle theta, how is r and theta, how are r, theta, and S related? Do you remember that? S is equal to r theta. If theta is in radians, that's exactly it. Because, what was the angle theta anyway? Radius is the ratio of the arc length to the radius. That's what your arc length is. When your S is equal to r, then you're at 1 radian. Okay, that's 57 some odd degrees, okay? So that's how they're related. So here's the formula, okay? So if we want to get this in terms of r of S, just simply solve theta as a function of r and S. And as I just said, theta is S over r, okay? So plug this in here, and you have r times the cosine of S over Ri plus r times the sine of S over Rj. Now that seems like we're running around in circles again, literally, okay? Now, let's take our derivative of that, r prime of theta, okay? only now it's going to be r prime of s. Okay, because r is a constant here, so this is going to be r prime of s. Okay, because that's the only thing that's varying. Your radius is fixed; it's not changing. Okay, so this will be that. So let's take the derivative of this one, and what do you get? R. Second. Okay, only it'd be a minus, right? Minus sine of s over r. But then you have to do the chain rule there. That would be, with respect to s, that would be 1 over r, right? The derivative of s with respect to r would be 1 over r, okay? Now here, plus r, that would be a plus. This would be cosine s over r times 1 over r, okay? And that would be your j component. So your r prime of s would be minus sine s over ri plus cosine s over rj. That's your r as a function, it's supposed to be an arrow there, as a function of s. Okay? R prime, yeah, there's my prime. I drew over my prime. I said, where did it go? Okay, now what is the magnitude of this supposed to be? It's supposed to be 1. And is it? When you take the magnitude of that, you will have the square root of this thing squared plus that thing squared, right? And what would that be? The square root of sine squared s over r plus cosine squared s over r. And that is going to be 1. So, this must be the arc length parameter because it's the only way you'll get a magnitude of r prime equal to 1. Okay? Now, is that where we wanted to go? That wasn't what we were trying to show, was it? Sorry. Yes, well, they showed that too. Okay? So, if its magnitude is 1, that's also got to be the unit tangent vector because its magnitude is 1. So here is going to be, this is also, where is it? Right here. This is also t of s, the unit tangent vector. Whoa. Yeah, because the magnitude, no, sorry about that, wrong one. Not r, but r prime, this one. This has to be unit tangent vector, oops, of s, not of r, okay? Now, why is that the case? Because it's in the same direction as r prime, unit tangent vector is, and its magnitude is 1, which we've just shown that its magnitude is 1, okay? So actually, we should have been doing this down here, because these are both 1s here. That's a minus, plus. So that is your unit tangent vector, okay? Well, the definition of curvature is the derivative of this with respect to s. So let's take the derivative of that with respect to s. So let me write it down again. This is minus sine s over r I plus cosine s over r j. Okay? So do our dt ds. So take the derivative of that, and what do you get? Derivative of minus sine is?
What problem are we trying to figure out?
Second?
Which one are we trying to figure out?
Okay.
Which problem are we trying to?
Okay, we're taking derivative of this unit tangent vector with respect to s. So derivative of this. Derivative of minus sine is? Negative, yeah. Derivative of sine is cosine, so the derivative of minus sine would be minus cosine of s over r. But then you have a chain rule, 1 over r, right? Derivative with respect to s would be 1 over r, right?
Will you take the respect of s every time?
What's that again?
Will you take the respect of s every time you're doing the general?
Take the derivative of this, is what you're saying?
Yeah, would you take the respect of s?
With respect to s, that's what we mean by that, ds. Okay, with respect to s. So it would be minus this, so the chain rule part would be 1 over r, right? Okay. So this would be the minus cosine s over r times 1 over r, okay? And and that would also be a vector, I, okay? And then the second part would be minus cosine, no, it's derivative of cosine, which is sine, okay? Minus sine, okay, because that was a plus there. And it'd be minus sine of s over r j, but then you have the chain rule, another 1 over r in front. So what that gives you is minus 1 over r times cosine s over r I plus sine s over r j. Okay. How are we doing on time? Whoops. Are we?
2 minutes over.
What's that?
2 minutes.
2 minutes to go. Okay. We're almost through with this. Okay. Wait a minute. Oh. Okay. We just did t prime of s. Okay. That's what that is. Okay. The magnitude of that, that's what we're looking for. The curvature is the magnitude of dt ds. Okay. So if we do the magnitude of that, that's the square root of 1 over r squared cosine squared s over r plus 1 over r squared sine squared s over r, okay? And again, factor out the square root of 1 over r squared, and you have cosine squared. I'm sorry, let me erase some space here so you can read. I'm not sure I can erase enough for you to read, okay? Still got some mess down here. I can't tell what it is. Okay. All right. Now, let's see if I can get this to show up better. 1 over r squared, factor that out, cosine squared s over r plus sine squared s over r. That would be 1. Okay, so you get the square root of 1 over r squared. The curvature is 1 over r. And that's exactly what they wanted us to show. That the curvature of a circle, k is equal to 1 over r. And that's true for any size circle. Any size circle. Okay. For the life of me, I don't remember what that was from, but, oh, I know what it was from. That was from my circle there. We have erased all that. Okay. Okay, so we've just shown the curvature is indeed 1 over r for any circle. So the smaller the circle, huge curvature. Larger the circle, small curvature. Okay, and that makes sense because in a small circle you're bending really quickly, in a large circle you're barely bending at all. Okay, an infinite circle would be a straight line, which would have 0 curvature. Okay, so where was that? That was, let's see what the next, oh, let me just go through these real quickly because they are going to show this. All right. Without loss of generality, you consider the circle to be centered at the origin, so that's what we did. X, Y be any point on the origin, blah, blah, got it. Okay. Letting theta be the central angle, you can say r theta is, yeah, got it, just like we did. Now, rewriting that as a function of s, from s is equal to r theta, theta would be equal to s over r, so that's what we did there too. And then we took a derivative of that, and you got that just like we did. So the magnitude of that was 1, so that makes it a unit tangent vector. So take that divided by its magnitude, and you just get the very same thing because it's a unit vector. The curvature is then the magnitude of that, the derivative. You take the derivative of that, which they didn't show you how they did it, but you know how they did it, and that gives you that for every point on the circle. All right, so we'll begin next time with this theorem 12.8. Okay, homework exercises here. Boy, this is sort of a long section. Any of the odds 3 through 7, they're all at calcchat.com. Try to do 9, that's at calcchat.com. Think you can do any of the odds 11 through 15, they're at calcchat. 13's at calcview. And I think you can do your 17 is at calcchat. Finding curvature, do either 19 or 21. They're both at calcchat. 21's at calcview. Any of the odds 23 to 27, they're all at calcchat. Okay. Any of the odds 29 through 35, they're all at calcchat. 33's at calcview. 37 or 39, they're at calcchat. And we'll hold off of those for a bit. That's as far as you need to go there. Okay. We'll pick up there next time. All right. Let me turn off my sound here.